here we go. Finally getting there. Okay, so this is something that you do in Math 3. We're doing polynomials of functions and complex zeros. I know that in my Math 3 class, I do not do a ton with complex zeros other than like letting kids know that they are there. I think that Miss Martin usually does much more because that's one of those places where she goes into a lot more depth than I do because she knows that you'll need it down the road. Whenever we're talking about zeros of polynomial functions, it tells us here that given a polynomial function, p of x, if p of a equals 0, then a is a 0 or root of p of x. So several things to pull apart here. First of all, we're using these words 0 or root interchangeably. When we're talking about the graph of the function, what does that look like? Where is a 0, right? It is where we hit the x-axis. It's an x-intercept. So your x-intercepts, zeros, roots, those are just words that can be used interchangeably, and they will do that. So questions that you see may use any of those three words, meaning for you to find the same thing there. And if we look at what the definition is really telling us here, it says if p of a equals 0. So you guys may not think this way much yet because I don't know how much you've been exposed to it in earlier classes. But when I see p of something equals a number, I immediately think of coordinates for a point. So like if I have f of 7 equals 2, 7 was the x-coordinate that got plugged in, 2 is the y-coordinate that gets pulled out. This is the point 7, 2, right? So when we see p of a equals 0, that is the point a, 0. So at an x-intercept, the a could be any number, right? What does the y-coordinate have to be? 0. So I'll kind of like to make myself a little note over here. At an x-intercept, y-coordinate is always 0. Hence the name 0 that they use often for these points. Okay. If a is a real number, so that a real number is any number that does not involve an I. So it can be positive, negative, fractions, decimals, even irrational numbers like square roots of like square root of 2 or something like that. Those are all real numbers. So if a is a real number, meaning it does not have an I with it, then if x equals a is a 0, then x minus a is a linear factor of p. So that phrase linear factor of p might be something you're not quite sure what they're talking about yet. So let's think back to all the times that we have talked about factors. In elementary school, you talk about factors when you're doing multiplication because your factors are the numbers you multiply together to get a number. So like some of the questions you may have had in elementary school might have been like, what are the factors of 10? The factors of 10 would be 1 and 10 or 2 and 5, right? The numbers you could multiply together to get 10, or you could think of them as the numbers that are will divide 10 equally. Whenever you get to Math 1, you start factoring quadratics. So that would be, just to give you an example, that would be like if we had x squared plus 3x plus 2. That could be factored into two binomials here. And so in this case, you'd have x here. What numbers am I going to have? 2 and 1, plus 2, plus 1, right there. So x plus 2 and x plus 1 would be those linear factors, right? They're the binomials that you're multiplying together. So in Math 1, you factor that way. In Math 3, you go further. 2, you factor again. It shows up again, but pretty much the same factoring. In Math 3, you do some more complicated factoring of polynomials. So there's a couple things, I'm not going to run through the whole thing, that you might do for this. This would be something like long division of polynomials to find your factors. So that would be like x cubed minus 2x squared plus 3x minus 5, something like that. And then you've got, maybe you're dividing that by x minus 5 to see if it goes into it evenly. And you had to do like, what number times x gives me x cubed? And that'd be x squared. And then I'd multiply that back. I am not going to go through all of that long process here. I'm just trying to refresh your memory. And you're not supposed to know every bit of it, but just say, oh, yeah, I've seen that before. The other way that I believe you guys also factored here is you did synthetic division. I don't do it in regular, but I believe that you guys did this where you have like 1, -2, 3, -5. You got like a little block out here that has a positive 5 in it. You do like bring the 1 down. 1 times 5 is 5. Add them together, you get 3. I'm not going to go through the whole thing of that either. Do you guys remember doing it? Not how to do it necessarily. You may not have, because you don't have to do synthetic division in 3. Yeah. Right. Yeah. Yeah. You probably, now long division is in the curriculum, so you're technically supposed to do it, although there's like one question and it's super hard, so some teachers skip it. I didn't spend much time on it. Technically, synthetic division can all be done with long division, so you don't have to teach synthetic division. It's not in there, but a lot of times teachers still do. And I know Miss Martin does this because it's quicker here. So what happens, though, with that is you can take something like x to the third minus 2x squared plus 3x minus 5, and you could break it down into x minus 5 times x plus 1 times x minus 3. You can factor it just like we factored over here, right? So those are a couple things that you've seen before. We're not going to go into great detail. I think we go back over some of this stuff right here, if I'm remembering correctly. But this is not where it happens, right? We just want to think about doing those things. So these linear factors are going to go with the equation for the function. So whenever we talk about zeros, we also must talk about their multiplicity. So a linear factor, x minus a, if a linear factor is repeated n times, the corresponding zero of the polynomial has a multiplicity of n. Typically, we know that the graph of a polynomial passes through the 0 on the graph. However, when a 0 has multiplicity greater than 1, the graph will behave differently near 0. So, if we look at this equation right here, they've graphed it over to the right-hand side. So we've got y equals -0.1 times x plus 4, x plus 1, and x plus 1 to the third, x minus 3 to the second. So first of all, let's look at where the zeros are on this graph. So you'll notice that we have one of them at -4. We have another one over here at 1, and we have a third one over here at 3. All right, so those are our zeros for this function. What do you notice about the zeros and the equation for the function? What do you think, Ryan? Mm-hmm. Squiggles a little, right? Okay, very good. what do you notice about the numbers you see here and the value of the zeros? What do you think, Zach? They're flipped. They're opposite signs, right? And as long as you have a simple linear factor, that's going to be the case. What's essentially happening here is you've got x plus 4. Like if you set that equal to 0, you would subtract 4 from both sides, so x would equal -4. So as long as it's a simple linear factor, that's what's going to happen right there. It's just going to be the opposite sign. So you'll notice right here, x plus 4, as Ryan was saying, only has an exponent of 1. It just crosses like you would think it would. At x minus 3, over here at 3, we've got a multiplicity or an exponent of 2, and we kind of like bump into the x-axis and go back down. And at 1, -1, we cross, but it kind of does this like weird squiggling whenever it goes through there. In fact, what could we call, -1's definitely a 0. What else does it look like it is for that graph? What other name could we give that point? We just did it in the last section. It looks like it's a point of inflection, right? You're changing concavity there. So that's kind of what squiggles it a little bit there. So your multiplicity of a 0 is the exponent of the factor that goes with it. And again, here you can see like you got your x minus 3 goes with +3. You can look at its multiplicity. Your x plus 1 goes with the -1, and your x plus 4 goes with the -4. So you have those zeros. X minus 4 has a multiplicity of 1. They didn't list it because it's just there once. X equals -1 has a multiplicity of 3. X equals 3 has a multiplicity of 2 for that. Okay? At x equals 3, the multiplicity is 2. The graph of the polynomial is tangent to the x-axis. And it says here the graph bounces off the x-axis. I know I use that a lot in Math 3, and I think Miss Martin does as well. That graph just like goes up, barely touches the x-axis, and goes back down. Right? We called it a bounce quite a bit. Of course, bounce is not an official mathematical word. The way you would say that mathematically, like if you were writing a textbook about this, is you would say the graph of the polynomial will always be tangent to the x-axis. So whenever it comes to like questions that they might ask you, they might say which 0 is tangent to the x-axis. They're not going to say which 0 bounces off of the x-axis, but you can think of those as the same thing right there. You are going to bounce or be tangent to the x-axis anytime you have even multiplicity. So if you have even multiplicity, the graph should bounce at that point. Okay? So let's skip down here. We probably only have time for A right here. If I'm looking at the equation of a graph and it's asking, or equation of a function, and it's asking me to find the zeros. The first one we're looking at here, we should be able to find the zeros pretty quickly. Who could tell me one of the zeros for A? What do you think? Let's see. Ryan, tell me one, and Zach, tell me one. Okay, x equals -1. What's the multiplicity for that one, Ryan? Good. So multiplicity of 1. Zach, what's another one? X equals 4. And what's your multiplicity on that one? 2. Right? There's another one. What is the third one? That one's a little bit tricky. It's 0. It's at x equals 0. And that comes from this. Oh, that's not the. That comes from this part right here. The -2 doesn't really do anything. It's the x, because if I could write it this way, -2, I could write it as x minus 0 cubed, like that if I wanted, right? So if I set that equal to 0, I will get 0 for that. So if you see an x just by itself, then you're also going to have a 0 at 0. What's the multiplicity for that one, Charlie? 3. Multiplicity would be 3 because that is what your exponent is. Very good. Oh my God, I think we got time to do B. For g of x equals 3 times x squared minus 4 times x minus 2 to the fourth, first of all, this just has a 3 right here. Are we going to have an x equals 0 here for this one? Is that going to be one of our? That 3 does not have a variable with it, right? So it changes the graph whether it looks like stretched out, tall, or short, but it does not give you any zeros. So you don't find anything there. X squared minus 4, you cannot find a 0 for it yet because it has the squared. So you need to factor that. Anybody remember how to factor x squared minus 4? There'll be two sets of parentheses. We'll have an x here, plus 2 and minus 2. It's a difference of squares. It's like one of those special cases. So we need to factor that first. And then you'll notice these two right here match, right? They're the same. So we could actually combine them, and we want to, so that we have our multiplicity correct. So we could write this as 3 times x plus 2 times x minus 2. What power on my x minus 2? 5. Whenever you have two things together there that have, you can combine, you add their exponents. So you'll have 5 of those there. So then we would say I have a 0 at x equals negative 2. That just has a multiplicity of 1. But my x equals positive 2 would have a multiplicity of 5. And that's as far as we're going to try to go today. So go ahead and pack